Alright, let's dive into the fascinating world of earthquakes by first understanding the theory of plate tectonics. This theory is crucial in explaining the movement of Earth's lithosphere and the formation of boundaries between tectonic plates. So what exactly is the Earth's lithosphere? Well, it's the outermost layer of our planet, comprising the crust and the upper part of the mantle. The lithosphere is divided into several large and small slabs, known as tectonic plates. These plates essentially float on the partially molten and more fluid layer beneath them, called the asthenosphere. Now, these tectonic plates are constantly moving, albeit very slowly, at a speed of around 1 to 15 centimeters per year. This movement is primarily driven by the heat generated from the Earth's interior, which causes convection currents in the mantle. As these currents rise and spread, they push the overlying tectonic plates, causing them to move. There are three main types of boundaries between tectonic plates: divergent, convergent, and transform. At divergent boundaries, plates are moving away from each other, creating new crusts as magma rises from the mantle. This is primarily seen at mid-ocean ridges, where new oceanic crust is continuously being formed. Convergent boundaries, on the other hand, occur when plates move towards each other. This can result in one plate being forced beneath the other, a process known as subduction. The subducted plate then melts and forms magma, which can eventually rise to the surface and cause volcanic eruptions. Convergent boundaries can also lead to the formation of mountain ranges as the two colliding plates push up Earth's crust. Finally, at transform boundaries, plates slide past each other horizontally. This type of movement can create intense friction, which can eventually lead to the release of energy in the form of earthquakes. In summary, the theory of plate tectonics helps us understand the movement of Earth's lithosphere and the formation of boundaries between tectonic plates. These movements and interactions between plates play a crucial role in the occurrence of earthquakes, which we'll explore further in the next sections. Now that we've covered the basics of plate tectonics, let's move on to the different types of fault lines and how their movements cause earthquakes. Fault lines are essentially fractures in the Earth's crust, where tectonic plates or sections of the lithosphere move relative to each other. There are three primary types of faults: normal, reverse, and strike-slip faults. First, let's discuss normal faults. These occur when the crust is being pulled apart due to tensional forces, causing one block of rock to slide down relative to the other. This movement typically happens along a sloping fault plane, with the hanging wall moving downwards and the footwall moving upwards. Normal faults are commonly found in areas with divergent plate boundaries, such as mid-ocean ridges and continental rift zones. Next up are reverse faults. These are essentially the opposite of normal faults and result from compressional forces that push rocks together. In this case, the hanging wall moves upwards relative to the footwall along a sloping fault plane. Reverse faults are often found in areas with convergent plate boundaries, like mountain ranges and subduction zones. Lastly, we have strike-slip faults, which are characterized by horizontal movement along a nearly vertical fault plane. This type of fault occurs when rocks slide past each other and there's no significant vertical displacement. Strike-slip faults are commonly associated with transform plate boundaries, such as the infamous San Andreas Fault in California. So, how do these fault movements cause earthquakes? Well, as tectonic plates move, stress builds up along fault lines. Over time, this stress can cause the rocks along the fault to deform and store energy. When the stress finally exceeds the strength of the rocks, they suddenly slip or break, releasing the stored energy in the form of seismic waves. This sudden release of energy and the resulting ground shaking is what we experience as an earthquake. In conclusion, understanding the different types of fault lines, such as normal, reverse, and strike-slip faults, and how their movements cause earthquakes, is crucial in studying the science behind these powerful natural events. Up next, we'll examine the concept of elastic rebound theory and the release of stored energy during an earthquake. Now that we've discussed fault lines and their role in causing earthquakes, let's examine the concept of elastic rebound theory. This theory is essential in understanding the release of stored energy in Earth's crust during an earthquake. Elastic rebound theory was first proposed by geologist Harry Fielding Reid in the early 20th century, following the 1906 San Francisco earthquake. The theory is based on the idea that rocks along fault lines can deform and store elastic energy when subjected to stress. This stress can be the result of tectonic plate movements or other geological processes. As the stress continues to build up in the rocks, they gradually bend and change shape, much like a rubber band being stretched. At some point, the stress becomes too much for the rocks to handle, and they suddenly snap back into their original shape. This rapid release of stored elastic energy generates seismic waves, which then travel through the Earth's crust, causing the ground to shake. And that's what we experience as an earthquake. Imagine you're stretching a rubber band between your fingers. As you pull it further apart, the tension increases, and the rubber band stores more and more energy. Eventually, the rubber band can't handle the tension anymore and snaps, releasing the stored energy in a sudden burst. This analogy helps explain the elastic rebound theory and the release of energy during an earthquake. One important implication of the elastic rebound theory is that earthquakes are cyclical events. After an earthquake occurs and the stored energy is released, stress begins to accumulate again along the fault line. Over time, this stress will once again cause the rocks to deform, store energy, and eventually lead to another earthquake. In conclusion, the elastic rebound theory provides a comprehensive explanation of how stored energy is released in Earth's crust during an earthquake. Understanding this concept is crucial for studying earthquakes and predicting their occurrence. Next, we'll learn about seismic waves and their role in the propagation of earthquake energy. Now that we've explored the elastic rebound theory and how energy is released during an earthquake, let's dive into the world of seismic waves. Seismic waves are the vibrations generated by an earthquake that travel through the Earth's crust and are responsible for the shaking we feel. There are three main types of seismic waves: primary waves, P waves, secondary waves, S waves, and surface waves. First, let's talk about primary waves, or P waves. These are the fastest seismic waves, and are the first ones to be detected by seismographs after an earthquake. P waves are compressional waves, which means they cause particles in the Earth's crust to move back and forth in the same direction as the wave is traveling. This movement is similar to how sound waves travel through the air. P waves can travel through both solid rock and liquid, making them capable of passing through the Earth's entire interior. Next up are secondary waves, or S waves. These waves are slower than P waves and arrive at seismograph stations after the P waves. S waves are transverse waves, which means they cause particles to move perpendicular to the direction the wave is traveling. This movement creates a shearing motion which can cause more damage than P waves. Unlike P waves, S waves can only travel through solid rock, not liquid, so they don't pass through the Earth's outer core, which is molten. Lastly, we have surface waves, which, as the name suggests, travel along the Earth's surface. Surface waves are slower than both P waves and S waves, but they can cause the most destruction due to their larger amplitude and longer duration. There are two main types of surface waves: love waves and Rayleigh waves. Love waves cause horizontal shearing motion, while Rayleigh waves create a rolling motion, similar to ocean waves. In summary, seismic waves play a crucial role in the propagation of earthquake energy. Understanding the different types of seismic waves, including primary waves, secondary waves, S waves, and surface waves, helps us better comprehend the nature of earthquakes and the potential damage they can cause. In the next section, we'll study earthquake measurement and monitoring techniques to quantify and track seismic events. Now that we have a solid understanding of the various aspects of earthquakes, let's move on to earthquake measurement and monitoring techniques. These tools help us quantify and track seismic events, providing valuable information for both scientific analysis and emergency response. We'll focus on three key aspects: the Richter scale, the moment magnitude scale, and seismographs. First up is the Richter scale, which was developed by Charles F. Richter in 1935. This scale measures the amplitude of seismic waves to determine the magnitude of an earthquake. The Richter scale is logarithmic, meaning that each whole number increase on the scale represents a tenfold increase in wave amplitude and approximately 31.6 times more energy release. For example, a magnitude 5 earthquake releases about 31.6 times more energy than a magnitude 4 earthquake. However, it's important to note that the Richter scale is mainly used for local and regional earthquakes and is less accurate for larger global events. To address the limitations of the Richter scale, seismologists developed the moment magnitude scale. This scale is also logarithmic and measures the total energy released during an earthquake. The moment magnitude scale takes into account factors such as the area of the fault that slipped, the amount of slip, and the rigidity of the Earth's crust. This scale provides a more accurate estimate of an earthquake's size, especially for larger events, and is now the standard measurement used by seismologists worldwide. Finally, we have seismographs, which are instruments used to detect and record seismic waves generated by earthquakes. Seismographs typically consist of a mass suspended from a frame with a pen or stylus attached to the mass. When the ground shakes, the frame moves with it, but the mass remains relatively stationary due to inertia. This difference in movement causes the pen to trace a pattern on a rotating drum or digital recording system, creating a visual representation of the seismic waves called a seismogram. Seismograms can be analyzed to determine the time, location, and magnitude of an earthquake. By comparing the arrival times of P waves and S waves at multiple seismograph stations, seismologists can triangulate the epicenter of the earthquake. This information is crucial for understanding the Earth's seismic activity and providing early warnings to affected populations. In conclusion, earthquake measurement and monitoring techniques, such as the Richter scale, moment magnitude scale, and seismographs, play a vital role in quantifying and tracking seismic events. These tools help us better understand the behavior of earthquakes, assess their potential impacts, and ultimately improve our ability to respond to these powerful natural phenomena.